So this is lecture 7, where we're going to talk about system classification. Before we start, a few words of feedback. So a few people have mentioned that they didn't do too well in the class test despite spending time revising or studying from the practice questions. And in a way, this isn't too surprising because I keep saying the practice questions, they're not intended for revision. So the practice questions are intended as an early test, as formative assessment, as a way to check how well you've understood. So the correct sequence is you should listen to or read the lecture. You should then try the problem sheets, because the problem sheets contain solved questions. There are also some pen casts. Some of these relate to the problem sheets and some of them don't. But after that, after doing all of that, you can take the practice test to see whether you're able to complete the questions in the necessary time, to make sure that your computer, that your browser is able to handle the graphics, is able to handle the question format, to familiarize yourself with the kind of questions that you're going to meet in the test. Then you have the test. And then following the test, there is feedback. So you need to follow this sequence, starting from the lecture all the way to the feedback. And don't ignore this final stage, the feedback. It is important. Okay, so unless you score 100%, you need to see what you did wrong. So spending time with the feedback is necessary. Now, where are we now? In week 7, so we finished speaking about signals. So all this first 6 weeks was about signals. Now we're going to talk about systems. So this is the second half of our module. And just like we started the module talking about signal classification, today we'll talk about system classification. So we're going to talk about the different types of system we have, the different words we use to describe them. What do we mean by a discrete-time system? What do we mean by a causal system? What do we mean by a invertible system? All of these things come under system classification. So really it's a simple kind of lecture. It's an easy lecture, just like signal classification was easy. And a quick reminder of how we got here. So last week we finished talking about signals and we introduced the idea of sampling as a first step in digitization. And I said we're not going to cover digitization in this module. We're just going to cover the first step, which is sampling. And the opposite of sampling is signal reconstruction or signal recovery. So we covered both ends there, and we spoke about Nyquist's theorem, which is it governs how fast we need to sample or how close our samples need to be to enable recovery to be perfect. We spoke about discrete time signals and their representation. And we had class test 3, but that was about the Fourier transform. It wasn't about sampling. And then we had a problem sheet with a whole bunch of pen casts. So there were probably twice as many pen casts as we had problems in the problem sheet. So I'll just add that here. So just to remind you, in lecture 3, we looked at the Fourier series, which applied to periodic signals that were continuous in time. And in weeks 5 and 6, or 4 and 5, we looked at the Fourier transform, which was for non-periodic signals or periodic signals that were also continuous. What we haven't yet looked at is discrete time signals. And there's a discrete time version of the Fourier series and a discrete time version of the Fourier transform, but we haven't included that in Elect 270. So just to let you know that these exist, but weren't covered in this module. So that's how we arrived where we arrived now. We took this route here. And that's the end of signals. So we still need to understand how signals work in order to understand how systems work, but we're not going to take any of these topics in greater depth than we've already done them. So in terms of where we are in the schedule, we're now at lecture 7. And the next class test will be on the 30th of November. And that test on the 30th of November will include the material from lectures 6 and 7. So sampling and system classification. Although they're not related, they're two separate topics, they'll both be combined into this one test on the 30th of November. Okay, so after today's lecture where we introduce systems and the nomenclature or the system naming approach, the words we use to characterize and describe systems, we'll then spend a week talking about the impulse response. We're going to link that to something called the Laplace transform. We'll then introduce the Z transform, and we'll spend 2 weeks talking about the Z transform. We're going to talk about the Z transform and the inverse Z transform. And in many ways, you'll find these 4 lectures easier than what came before. So that's just setting the scene. Now we'll start by actually introducing and defining systems. So we already defined a signal as a measurable variation, a measurable change in a quantity that conveys information. Now a system is anything that manipulates one or more of these signals to accomplish some function producing new signals. Okay, so for any system, we expect there to be an input and an output. You can have more than one input, and you can have more than one output. But we will generally have one output, or we'll look at systems with one output in this module. That's not a condition, it's not a criteria, but to keep things simple, we'll try to characterize systems that have one input, so one output, and try to keep the inputs down just to one. But you can always have more than one input. So if a system was adding inputs together, you'd have to have x1, x2, etc. So we're going to try to have one output and, where possible, one input, but not necessarily. So remember, we came across the words analysis and synthesis when we spoke about the Fourier series. And we said analysis is where you break something down, and synthesis is where you build something, where you construct something. In the same kind of way, we'll analyze systems by analyzing the output when we know what the inputs are. And system synthesis is where we have both the inputs and the outputs. And we'll look at these in a little bit more detail as we progress. So systems, just like signals, were around us all the time, and we said anything can be described as a signal. In engineering, or just in general life, systems surround us all the time. They can be purely electrical systems, like an electrical circuit. They could be biological systems, because they too have input signals, and they manipulate the signals somehow, and they produce output signals. So they are systems. They can be a combination of biological systems and electromechanical systems. So it could be a mechanical system or a micro electromechanical system. It could be a control system. It could be a communication system, a satellite system. It could be an audio-visual system. It could be an instrumentation system. All of these things, anything really that you study or you build at university as part of this course is going to be some kind of a system. And what we're going to look at today is just the kind of language we use to describe these systems. And we're not going to go into it in great detail. We're going to take 4 or 5 of the most important characteristics, and then we'll try to understand what they mean, how they apply, take some examples, and then move on next week to talk about the impulse response. So, the first thing we often refer to is a continuous time system. So we've spoken about continuous time signals, and a continuous time signal is one that's defined for all values in time or all instances in time, not only at particular instances in time. And a continuous time system is where both the input and the output are continuous in time. So continuous input, continuous output, we call that a continuous time system. You can also have, as you would expect, a discrete time system, where you have a discrete time input and a discrete time output. We call that a discrete time system. So those are the easiest definitions in the world. Now some characteristics or properties of systems. And we're going to look at causality, linearity, time-invariance, and a couple of others. Why are these characteristics important? Just like it was important to describe signals as being periodic, non-periodic, causal, non-causal, analog, digital, deterministic, random, it's important to be able to describe a system so that we can describe how they work, describe their real-world implications. So using these words, causal, linear, time-invariant, they tell us how these systems behave and how we can exploit and analyze these systems. So the first characteristic we use is linearity. Now, where have you seen this before? We saw this when we spoke about the Fourier transform. We spoke about a property, and we called it the linearity property. And at the time, I told you that combines 2 characteristics or 2 properties, additivity and homogeneity. And additivity simply means that if you have 2 signals, x1 and x2, as inputs, then so if x1 gives you y1 and x2 gives you y2, then adding the 2 should add the 2 outputs. So the sum of the 2 inputs should give you the sum of the 2 outputs. So for example, for the Fourier series or Fourier transform, we said x of t plus y of t correspond to x of omega plus y of omega. So that satisfies the additivity property. So we can say the Fourier transform is a additive system. Homogeneity is where we introduce coefficients here. So it's no longer simply adding x and y. We're now adding weighted multiples of x and y. So ax1 and ay1. So it means if you take a signal and you multiply it by some constant, then the output should be the same as if you were to take the output x to give you y and then multiplying it by a. I'll explain this a little bit more clearly with a diagram, a block diagram in the next slide. But basically, the combination of these two properties, additivity and homogeneity, that gives you something called linearity. Okay? Or superposition. So this is what you're familiar with from the Fourier transform linearity property. Now, using a block diagram as an illustration, if this was my system and I applied a signal x1 to the input, I would expect some output y1. And if you apply x2 to your input, you'd expect some output y2. But if I were to add x1 and x2 and input the sum of these two signals, so I've got my first signal and my second signal, and I add them together, what is the output? Compare that to another system where I take x1 and I apply it to the system, I take x2 and I apply it to the system, and I take the outputs and I add the outputs together. So here what I have is y1 and y2 added together. Whereas here I added x1 and x2 and I put those into the system. Now, an additive system will have the same outputs. So if what I get here is the same as what I get here, that's called an additive system. It means it doesn't matter if you add the inputs or you add the outputs. So if adding the inputs before the system gives you the same output as if you were to add the two outputs of the two inputs, such a system is called additive. Now, homogeneity, or a homogeneous system, is different. A homogeneous system is where, so for example, if I had a system where an input x gives you an input y, or x1 gives you y1, and if I took the same system, so this is the same system, this system is unchanged. If I took the same system and instead of just applying x1, I multiplied by some constant a. So the input is actually ax1. The output would be a times y1. So what I'm comparing is these two outputs. If I take my input x1 and I multiply it by some constant and I apply it to the system and I get an output, will it be the same as if I took my input x, I applied it to the system and then multiplied by a? So a before or a after? Will this output be the same as this output? If they're equal, it means that this system is a homogeneous system. So the test of whether something is homogeneous or not, or the test of homogeneity, is to see whether the output is the same whether you multiply by your constant before or after the system. A very different characteristic of a system is causality. A system is called causal if it doesn't anticipate future values of the input. That means the output only depends on present or previous values of the input. The output depends on present and previous values of the input. And that's almost obvious because all real-time systems have to be causal. No system can anticipate a future input. So no system can have an output that depends on an input that hasn't happened yet. Okay, just imagine a system that can give you an output depending on an input that hasn't happened yet. So if I said a system has an output y that depends on x 1 second ago. So t minus 1, that means 1 second ago. That means in the past. Whereas y of t, that means now. The output now. So the output now depends on the input 1 second ago. And that's absolutely fine. That's a causal system. What's not okay is to have a system that depends on a future value. So x of t plus 1, that's a future value. That's a value that hasn't happened yet. So if y of t is related to x of t plus 1, that is in the future. So that's a non-causal system. So no system can be non-causal. We can, of course, describe mathematical systems as being non-causal, but no real physical systems can be non-causal. So let's take some examples. If y of t equals x squared of t minus 1, is that causal or non-causal? So y of t, that's the output now. X of t minus 1, that's 1 second in the past. So can the output now relate to the input 1 second in the past? Yeah, absolutely. Why not? So, for example, y of 5 can depend on y of 4, and that's absolutely okay. So that is a causal system, and that's absolutely okay. What isn't okay is to depend on a future value. So that is a future value, so that is not okay. So that's a non-causal system. Now, if y of n depends on x of minus n, it's not so obvious because x of minus n, is that in the past or in the future? So minus n is in the past if n is positive, but it's in the future if n is negative. So for example, if we said y of minus 5 equals x of 5, x of 5 is 10 seconds after y of minus 5. So that's a future value. So as long as there exists some value of n or some value of t for which this is in the future, therefore we call it a non-causal system. Let's look at this final example. Look first at what's inside the brackets. So this bit, this is what we're most interested in. What value of x are we interested in, or what time is x? What is the value of x for, what is the value of time for which we are using x when finding y of n? So you would notice here that n minus 1 is less than n. So therefore, we would call that causal. Now you might have noticed that there's an n plus 1 here, but that's just a number. N plus 1 is a number. That's not the future. That's not the future. So for example, if the time is 9 o'clock and I said 9 plus 1 equals 10, that's not the future, that's just a number. It only becomes a problem if I were to say x of n plus 1. Now it's a problem because that's the future. But simply saying n plus 1, that's not the future, that's just a number. Okay, so we're interested in this bit, we're not interested in that bit. So this is a causal system. Now this is one of the less easy ideas to describe and to explain, and it's the idea of time invariance. A time invariant system is a system whose behavior is independent of time. That doesn't mean that the output doesn't change with time. The output will naturally change with time, but its behavior doesn't depend on time. So the way in which it responds to an input doesn't change with time. So for example, if you have a calculator, that's an example of a system, and we call such a system time invariant because you would expect the calculator to behave in exactly the same way, independent of time. So if it was 9 a.m. and you calculated the square root of 100, you would get 10. And if it was 5 p.m. and you calculated the square root of 100, you should also get 10. So the fact that the time has changed shouldn't change the way it behaves. So it's not changing. So it's called time invariant. So time hasn't affected the way it's behaved. So if the input x is going to give you the output y, so if the input 100 is going to give me the output 10, then delaying that input, I've delayed it by 8 hours, should give me the same output, just delayed. Okay? So this is an input giving me an output. This is a delayed input giving me a delayed output. So a time invariant system, or a TI system, will follow that rule. And we're going to look at how to test whether a system is time invariant or not in a second. So we call this test the test for time invariance. It's to see whether or not a system is time invariant. And we use these block diagrams just for illustration. So we're looking at a system, and I've simply repeated that same block for the same system 3 times. So the same input is going into all 3. So this is my input x. It gives me some output y, and let's call that y1. So for my calculator example, my input is 100 and my output is 10. The system is calculating the square root. Now, if I were to delay the input, so it's still 10, it's just delayed. So it's an input that's been delayed by a few seconds, minutes, hours. So we call that now x of t minus a. So that minus a, that is a delay. Okay, it's a delay by a seconds. Now, it doesn't matter if a is negative or positive. What matters is it's a shifted version of the input. So by delaying the input, I get some output. Doesn't matter what it is. I've delayed my input and I have some output. If I were to take my output, which I had got here, and delayed it by a seconds, if these two outputs are the same, we call that a time-invariant system. So again, if you take your input, delay it a little, and see what the output is, and then try, instead of delaying the input, delaying the output, and then recording that. And if these two are the same, i.e. the delayed output, if it's the same as the output for a delayed input, we call that a time-invariant system. Again, if the delayed output is the same as the output for a delayed input, we have a time-invariant system. We're going to look at a couple of examples. So let's look at this example. The output, y of t, is equal to t multiplied by cosine of t. Now, before doing the test of linearity, before we even go there, let's just look at this. Just by looking at it, we can tell that the output doesn't just depend on the cosine of the input, because this is your input, and this is your output. So the output doesn't depend only on the input, it also depends on time. So if time is 0, the output is 0. If the time is big, the output will be multiplied by a large number. If the time is negative, the output will be multiplied by a negative number. So the output depends on the time. So I can't call it time invariant. It's clearly time variant or non-time invariant. We can conclude that just by looking at that. But if we wanted to actually carry out the test, remember we said the test is the delayed output the same as the output for a delayed input? So let's try. This is my input, and this is my output. So this is the original. That's this first line. Input, output. Now what I'm going to do is I'm going to find the output for a delayed input. So the input will be delayed. So instead of having x of t, I'm going to have x of t minus a. That is the delay. So it's a delay in the input, so it's a delayed input. So I'll call that y2. Now I'm going to find the output, sorry, the delayed output. I'm going to take y of t and I'm going to delay it by a seconds. And delaying the output means replacing every t with t minus a. That t becomes t minus a. So in calculating the delayed output, you replace every t with t minus a. Now, my test is to see whether this and this are the same. Sorry, this and this are the same. So this bit, it looks the same as that, but here I have t, and here I have t minus a. So they're not the same. So it's not time invariant. And that's what we said at the beginning when we saw that t up there. So this is how you would apply the test for time invariance. You would try to delay the input and see how that would affect the output. And then you'd try just delaying the output. And then you'd compare the two. So mathematically what you would do is you'd replace x of t with x of t minus a. And then you'd try replacing t with t minus a. And then you'd see if these two are the same. Same example, block diagram. So this is my input x, this is my output y. And there's a t, and there's my x of t. If I were to delay x, that's my delay, I'd have x of t minus a. And if that is my input to the system, the output is t multiplied by cosine t minus a. Because that's the definition of my system. It takes time and it multiplies it by the input. And the input happens to be delayed. Whereas, if I were just to take this output and delay it, it would mean replacing t here and here with t minus a. So these two are not equal, and therefore it's not time invariant. A few more examples, but these are straightforward. These are really easy. These you can just tell. So here you have your output is a function of a future input. But you can probably tell immediately that if you were to delay the input or delay the output, the only thing that's going to change is that's going to have an a subtracted from it. So it is time invariant. This one here is non-time invariant because there's that t there. So it depends on the time. So if t equals 0, if you have a 0 here, y of t is going to be 0. If this is big, this will be big. If this is negative, this will be negative. So it depends on time. Or you can say, if I were to subtract a from this, or subtract a from this and this, they wouldn't be the same. So these are continuous time, and these are all discrete time. So here you have the output is equal to the future input plus 5. 5 doesn't change with time, neither does this. So that's a time invariant system. This one, less obvious, it's non-time invariant, and you can probably imagine why. So the output at any point in time is equal to 5 plus x of 2n. So think how you would apply this block diagram to this. There'll be a number of pencasts where I'll go through a few dozen examples of time invariant and non-time invariant and linear and non-linear systems, and you'll see all of these. But just think for a second, why would this be time non-invariant? So remember, we have two tracks. We have a delayed input and we have a delayed output. So if we were to delay the input, we would simply subtract a here. But if we were to delay the output, we would replace n with n minus a. So you'd have 2 times n minus a, whereas in the first case, you'd just have 2n minus a, so it wouldn't be the same. The same here. This is clearly non-time invariant because it depends on n. Anything where n is explicitly part of the expression and not part of the independent variable suggests it's going to be non-time invariant. And again, if you delay the input, it means you're going to subtract a here. But if you delay the output, it means both n here and here you replace them with n minus a. And same here. E to the minus n, what matters is there's an n there. And that isn't treated the same way as that. So that's the independent variable, and if you delay x, that will become n minus a. But if you delay y, both this and this become n minus a. So that's non-time invariant. As I said, so time invariance isn't an easy concept to grasp, so you need to go through several examples to really get the hang of it. But there are plenty of examples in the problem sheet and in this week's pencasts. Another system characteristic, or another way of describing systems, is whether a system has memory or not. So a dynamic system has memory, a static system doesn't have memory. Now, a system has memory if the output depends on anything other than the input now. So y of t is the output now, and x of t is the input now. So if the output depends only on the input now, we call that a memoryless system. So it's like a resistor. A resistor, the current in the resistor will depend on the potential difference across the resistor now, and only now. It doesn't remember anything from the past. So we call that a system with no memory. A system with memory is where the output now depends on any value other than the input now. So any past or future value of the input. So if I said, for example, y of t equals x of t minus 1, that is in the past. That's a past value. And if I said t plus 1, that is a future value. So as long as the output now depends on anything which is not x of t, that is called a system with memory. So, examples. A resistor, we said, only depends, so y of t only depends on x of t. So that is static. Okay, so memoryless. A capacitor, on the other hand, the y now depends on the integral of the input from minus infinity to t. So that includes y of t or x of t, but also includes previous values. So that is the past. That's history. So as long as it's invoking previous values of x, we say this system must have memory. So we call this a dynamic system. Okay, a unit delay. A unit delay, the output now is equal to the input one sample ago. So that's past. So if the output now depends on a previous input, that system must have memory. So that's called a dynamic system. An accumulator simply adds up the inputs. So in this case, it's adding up input from minus infinity all the way to n. So the output now is equal to the input now plus previous values of the input. So clearly, that's also a dynamic system, because all that is in the past. So it means the system has to remember what the previous values were in order to add them up. So the only the only static system here was the resistor. The final characteristic I want to describe is something called invertibility. Now, an invertible system is a system where an input X can give you an output Y, but as long as it's possible to create a system that will take that Y and uniquely give me back my original X, as long as this inverse system can exist, then this original system is called invertible. That means I can invert it. So for example, if I said y of t is 4x of t, that means the input is multiplied by 4 to give you the output. I can invert that. I can say, well, if I take the y of t and divide it by 4 to find w, that means that x gives me y, and then y will give you w again. W will equal x. So these two are inverses. So that is invertible. Another example. If I said y of n is, so this is the accumulator again. It's adding up previous values of x. Is it possible to invert that? Can I recreate x from y? Well, from any one value of y, you probably can't recreate x, but if you have enough values of y, you can subtract two consecutive values, and you can recreate x. So all of these systems actually are invertible. So invertible applies to all three of these. So all of these systems are invertible. The final example is an integrator. So an integrator can be inverted using a differentiator. So again, here we have continuous time, discrete time, continuous time. So it doesn't matter. All of these definitions and characteristics apply almost equally to both continuous and discrete. Another example. If a system is described by a square operator, so y of t equals x of t squared. So if x of t is 4, y of t is 16. Is that system invertible? Is it possible to design a system that will take my 16 and will give me 4 again? So you might think, oh, we can use a square root operation. But it's not that easy, because that's what that looks like if you have x and y. And clearly, two different values of y, so different values of x, can give you the same value of y. So it means that minus 4 will also give you a 16. So it's not possible to find a system that will take the 16 and give you the minus 4, because we wouldn't be able to tell exactly whether the input was minus 4 or 4, because we don't have a one-to-one mapping. What we have is a many-to-one. Compare that to an exponential. So in this case, you have something like that. That's your x, and that's your y. So for any given value of y, you can find x, it's possible to design a system that will give you your original value x from y. So this is w, that will be equal to our x. So it's possible to do that here, so we call this invertible. It's not possible to do it here, so we call that non-invertible. And there will be more examples that you can look at in the problem sheet. So that's all for this week. In summary, we've looked at different terms that we use to classify systems. We looked at linearity, and we said linearity encompasses additivity and homogeneity. Or I should say homogeneous. We looked at causality, and we said a causal system is a system that doesn't anticipate a future input. We looked at time invariance, and we said that's where delaying the input and delaying the output give you the same result, i.e. the output or the behavior of the system doesn't depend on time. It can change with time, the output can change with time, but the way it deals with the input shouldn't depend on time. We distinguished between a system that had no memory, static, to systems that did have memory, dynamic systems. So static, dynamic, memoryless, memory, same thing. So let me write that. So that's memoryless and memory systems, or systems with memory. And finally, we just spoke about systems that were invertible as opposed to systems that weren't invertible. Okay, so that's the end of today's lecture. We have a problem class on Monday and a problem sheet on Thursday/Friday. And don't forget, our next class test is on the 30th of November, and that will include lectures 6 and 7. Okay, I hope you found that helpful, and until I next see you, I hope you all stay safe.